So what we're going to do today is talk about the very beginning material on the physics and chemistry of radiation biology, sort of what happens when radiation intersects with matter in some way. Uh, as I often point out, this was an early little book from the 1960s put out by then the Atomic Energy Commission, now the Department of Energy. And you can see that safety guidelines have changed significantly since then. Here's the author, Norm Frigerio, who is smoking a pipe as he is injecting a bunny with radionuclides. You can see his foam badge, no lab coat, and the Geiger counter here checking for it. So safety regulations have changed a lot. A lot of the basis of what we know about radiation came from these early days of study, and we will come back to it, although radiation biology is ever evolving and ever changing. To give a bit of history, the first, Röntgen discovered the X-rays. You got to know Röntgen. 1895 was the big year. The first, they obviously saw the promise of this immediately. The first patient was treated with radiotherapy a year later. And as one of my friends, Chris Keel, likes to point out, the first lawsuit was also filed that very same year. In the 1910s, we have the widespread use of radiation in the clinics. By the 1920s, we can measure radiation, and we developed the concept of fractionation. So just look, from 1896, when patients are first started, until 1920s, we could not measure radiation. So when they were giving radiation to people, it was a very iffy proposition. They had no idea about dose. First, cobalt machines are introduced in 1951. We can now measure the effects of radiation in tissues. And then finally, in 1953, we have the LINAC introduced, which sort of ushers in the modern age of radiation oncology. In terms of, I got these slides from Elaine Zeman from Röntgen's early discovery. Here's Röntgen. Here are the early images that existed of radiation devices. You can see that they're very primitive, no approach to collimation. They just are able to emit radiation. They were very low energy. And, almost every quack who wanted to play with radiation could have access to it. Here's the first publicly available radiograph. It was taken by Röntgen himself. Supposedly his wife with her wedding ring on. It's displayed in the Röntgen Museum in Würzburg. I actually saw this live in Würzburg, which is where Röntgen had worked and did his studies in Würzburg, Germany. Okay, let's look at radiology. There are a couple of things we need to know in here too. Radiology also begins with Röntgen, but here I note that he got the Nobel Prize for his work in 1901. College finally introduces the hot cathode tube. In 1918, Eastman of Eastman Kodak fame from Rochester, New York, introduces the first X-ray film into to be used in the clinic. And finally, in 1930s, we have doctors that are actually split into those that are giving therapy and those that are doing diagnostic radiology. I will note that of these, there are still some departments that haven't split these two, in fact. And with more image-guided therapy, there might be reason to keep them together. In 1950s, we have the image intensifier that exists. In 1956, ultrasound is first used. In 1967, MRI is used. And finally, in 1972, Cormack and Hounsfield received the Nobel Prize years later, but the work that they did was in inventing the CT scan. And we will talk later about Hounsfield units, which are used to measure CT intensity. That's actually a board's question. And then finally, let's throw in nuclear medicine here. Becquerel was the one who's credited for discovering radioactivity. Barkla did characterize the fact that many of the elements are naturally radioactive. You have the Nobel Prize for that. In 1931, Lawrence develops the cyclotron, and this leads to the first synthesis that ever existed of radioactive elements. In 1937, the first patient is treated with what they called artificial radioactivity at the time, which is really this synthetic radioactive elements. The first treatment was leukemia at UC Berkeley. In 1946, we see a patient with thyroid cancer being treated with radioactive iodine for the first time, and we still treat thyroid patients with radioactive iodine. Um, Xenon 133 was used in the lungs to be able to visualize the lungs, and finally, in the 1970s, we can see almost every organ of the body. And I would just like to note that there was this explosion that happened in 1930s, 1940s, and that was mostly associated in part with the radiation work that was being done for the development of the bomb that led to, as a byproduct, much of the clinical work that we know now. Here is Pierre Curie, who put a radium tube exposed his skin, and he's going to Becquerel and saying, hey, will you watch this? And this is the first recording of normal tissue toxicity that was being evaluated over time in a dose-responsive way. It's sad, but that was the way science was done in those days, is you did it to yourself and then you put it on other people. Just a few images to kind of put this in perspective. Here is, actually, this is the radiologist. He's put his hand into the beam here in order to calibrate it for the patient that's sitting out in the waiting room someplace. The technologist is going to take an image of it all through the camera. And this was the very best that we had. Notice, no collimation. Everybody in this room was being exposed. And the incidence of cancer is going to be much higher in radiologists here in the 1920s. Here is a patient being treated with radium for a brain cancer. In these ampules is radium. He's got a brain cancer here. They knew the radium could cause cataracts. They weren't so sure it could cause cancer. So because of the cataracts, he's wearing these special glasses to be able to protect himself. But notice that the kind of penetration we're getting into the brain, this had to be put very close to the tumor because we couldn't target very well. Finally, the supercharged sphere is developed, and this was a precursor to the LINAC. Here's the physicist who is injecting electrons into the supercharged sphere. This then leads to the patient being able to be treated for their tumor. And then finally, here is a patient who has a head and neck tumor here. Here's the radiation in the chamber. Now we've got a shutter. So you could open and close the shutter to be able to expose it. And this is our image-guided therapy. You move this arm around all over the place to give you the best location for the tumor. So you can see these were very primitive ideas that came out, but they made us, but they all gave rise to where we are today. Just some stamps of the times, Röntgen, memorialized in Spanish stamp, Becquerel, and the Curies for the work that they had done in radiation. To give you an idea of how primitive it was, these are some of the early radiation devices. This one's being put entirely on the face. Here's a person being treated, again, put almost on half the face. These devices were very, there was no collimation. There's lots of exposure going on in this room. So people are getting exposed. There was lots of injury. People lost hands, fingers. And in Hamburg, Germany, there's a memorial honoring radiation workers whose lives were, whose deaths came about from these early radiation exposures. They did not know how dangerous it was that they were working with. The methods for delivering radiotherapy are pretty standard these days. Mostly we use external beam, where we give the radiation to the body through this external beam. Brachytherapy we'll talk about in here a little bit. It comes from the Greek word brachy, meaning short range, where we're delivering the radiation using some sort of implanted device. Radiosurgery and gamma knife are tied together because they use these multiple pinpointed beams to get a very focalized exposure at a given place. And then there's intraoperative radiotherapy, where radiation is delivered during surgery. We'll also have an alternative treatment section where we'll talk about protons, carbon ions, other heavy ions, and even we'll at least briefly mention flash as a new delivery method as well. So one of the important aspects of radiation is that we deliver energy that depends upon the mass of the person. So for a 4 gray dose, which is near the lethal dose to kill 50% of the population in 60 days, for a mass of 70K person is going to give us about 67 calories of energy. To get that same amount of energy, were it in thermal energy, it would be the equivalent of drinking 1 sip of very hot coffee, or in mechanical energy, it would be equivalent to lifting a person off the ground, that weighs 70 kilograms off the ground by 16 inches. So you can see that this radiation is about energy. We're going to learn about some other kinds of damage that are done that don't require energy, but radiation does. So now finally we get to what's the official definition of ionizing radiation. And here it is right here. An ionizing radiation is anything that causes the ejection of one or more orbital electrons from an atom. So if it's capable of causing an ejection, it is called ionizing. If it's not, it's non-ionizing radiation. We also have excitation, where the energy is the electron is raised to a higher energy, but it's not necessarily ejected. That excitation is going to give rise to heat and light, but it won't cause ionization. It won't cause the same degree of damage. The types of radiation fall into both the electromagnetic type and the particulate type. In the particulate category, protons, electrons, alpha particles, beta particles are all charged. Neutrons are not charged, but these particulate radiations are all falling in the category of being ionizing. In the electromagnetic spectrum, only gamma rays and X-rays are ionizing, all the rest are not. Even though ultraviolet can cause much damage through crosslinks, it is not an ionizing radiation. Radio waves are not ionizing. These qualities of radiation do not cause ejections of orbital electrons, and therefore do not break covalent bonds through their energy. There's a board's question that asks about cell phones, which obviously generate radio waves, and their role in cancer. And you answer on, no matter what you personally believe, that cell phones are not associated with an increased incidence of cancer. What you need to know here is that radio waves have low wavelength, have high wavelength, low frequency, low energy, whereas X-rays, gamma rays have low wavelength, high frequency, and high energy. And I would memorize these in this order, as I've seen them sometimes say, which of the following is the correct listing of electromagnetic spectrum in terms of decreasing wavelength, frequency, and you need to know that. I think I've said all of this. And I'll emphasize again, ionizing radiation does not include sound or radio waves, visible infrared, or ultraviolet light. So let's compare and contrast, first of all, X-rays and gamma rays. X-rays are produced from an atomic nucleus outside of the nucleus. They're generated extranuclearly. They are atomic. They are usually produced by an electrical device that takes electrons, accelerates them to a high energy, and then stops them. And it's usually the kinetic energy of motion that's important here. This is in contrast with gamma rays, which actually have intranuclear production. So therefore, they're produced from within an atomic nucleus. They're emitted from radioisotopes that are, any atom that is radioactive can emit some type of gamma ray, or some cases they emit alpha particles or others. But if it's a gamma emitter, it will emit. And the excess energy of the electron is what is important here. Here's the old-fashioned X-ray generator. We've got the cathode here, the anode here. The electrons are negative. They're moving toward the positive pole. As they're moving, they hit a target. This target, when bombarded by electrons, generates X-rays, and so we see the development of X-rays. Well, the modern LINAC is based on a very similar concept. We have electrons being shot in with an injector, being accelerated through a bending magnet, hit a foil or a target. This then causes the X-rays to be released, which we can then collimate them so they come to very pinpointed beams. So the LINAC is based on the same thing as the old-fashioned X-radiator. And if we now look at what's the official definition of ionizing radiation in yet another way, comparing energy and wavelength, it's anything that has a photon energy of greater than 124 electron volts and a wavelength of less than 10 to the minus 6 centimeters, which hits about here. Now you're going to see some ultraviolet radiation that fits into this category. This ultraviolet radiation is not the type that's found on Earth. Ultraviolet radiation is not ionizing, and none of these other radiations are ionizing either. Here's a diagram that shows where we might encounter some of these. Where we're going to encounter ionizing radiation, X-rays, and gamma rays, going to be mostly in medical exposures, but also in our environmental exposures. We have, as we're sitting outside lapping up the rays, we're also getting some galactic cosmic rays that are coming through, and some of those contain gamma rays and X-rays, actually more often gamma rays. Cosmic rays are what astronauts encounter in space, but many of them go through the Earth's atmosphere, and we can be exposed to some of those as well. UV radiation, which, as we said before, is not ionizing. We're likely to get it from the sunlight, from a tanning booth. What does ultraviolet do? It causes cross-linking of DNA, and so therefore it can cause cancer because of that cross-linking. Visible light is here. Infrared we might experience in a heat lamp. Microwave is going to be from the microwave oven. TV, radio waves, and then finally extremely low frequency. And I will say again that none of these have been associated with cancer induction, except perhaps from a thermal perspective. So microwave, the heat is so great that it can cause irritation that might lead to a cancer, but this is only from thermal, it's not from the radiation itself. Gamma radiation is very similar to X-rays. It usually travels as packets of radiation energy, but it also travels as waves of energy. So it travels at the speed of light. There is no charge. They're emitted from an atomic nucleus, and they frequently occur with alpha and beta decay as well. Beta decay is going to usually involve an electron, and alpha particle is usually going to involve two protons and two neutrons. I don't think you need to know this, but if we ever need to know the definition of the electron volt, here it is. And as I said before, X-rays can travel as waves or streams. When they travel as waves, they follow that old physics formula, the velocity equals the wavelength times the frequency. When they travel as streams, then they follow this formula, which is lambda equals the 12.4 over the energy. The constant is 12.4. And you'll remember before we said, let's just go back and pick it up. Here it is, 124 electron volts. That's where that comes from, is from that number. Oops, sorry, I'm going. Okay, so we talked about gamma rays and X-rays. Let's go into particulate radiations. Electrons, of course, you learned this in grade school, are small, they have a negative charge, and because they're charged, they can be accelerated to high energies. In fact, anything that's charged can be accelerated. The proton is 2,000 times the mass of the electron, much more massive. It has a net plus charge, unlike the electron, which has a net negative charge. The alpha particle is the nuclei of helium atoms. It's got two protons, two neutrons. It's got a net 2 plus charge. Where will we experience alpha particles? Well, we'll experience it in the Earth's crust, where our uranium is releasing alpha particles, where our radon is releasing alpha particles into the environment. We might encounter it in some of our radionuclides that we're using clinically, particularly those for brachytherapy, and we'll talk about those a little bit later. But therefore, the alpha particle is a net 2+ charge. The neutron is interesting because it has the same mass as the proton, but it has no charge. So therefore, it can't be accelerated. What was the neutron most famous for was the fact that it could split atoms. So when they first took the uranium-239 atom and bombarded it with neutrons, they were shocked when they got barium products, which meant that the neutron was able to split the atom, and that became the basis of the atomic bomb. If it's heavy charged nuclei, it can be produced by accelerating ions. We'll look at that later. Here are just the data on the weights of these subatomic particles. And now I need to mention another concept. When neutrons interface with matter, neutrons are not charged. What happens is the neutron releases a proton called the recoil proton, which is charged. So much of the damage from neutrons might come from these recoil protons that are being released. So even though the neutron enters the matter, it's often the proton that's causing the damage. In the case of photons, often the photons come into the matter, but it's the ejected electron that's causing the damage. And I'll show you some of those reactions in a bit. Here's the concept. We've got this DNA molecule, and when the electrons from recoil protons, so here are recoil protons being released, you have these many places where it can interact with matter. This is very densely done because it's a high energy radiation. This is more loosely done. These are electrons, but they too can interface with the DNA and cause damage within the DNA. We will hear later, but I'm going to introduce this concept now because it will be helpful to us. We usually divide radiation into high LET and low LET radiations. Clinically, most often we are using X-rays, gamma rays, protons. Those are all low LET. In some places in the world, they're using carbon ions and helium ions and neon ions, and those are high LET radiations. Astronauts, when they go into space, are encountering high LET. When we do brachytherapy with alpha particles are considered to be high LET. LET means linear energy transfer, and it's the amount of energy that's deposited per unit distance that a track travels. So why does it matter to us if it's high LET or low LET? Well, the idea is that for the same dose of radiation, high LET radiation causes much more damage per unit dose than does low LET radiation. So for our intents and purposes right now, we're just going to talk about it as low and high LET, realizing that low LET is gamma rays, X-rays, protons, and high LET is carbon ions and alpha particles and other types. And we will have a whole section on LET to explain that in greater detail later. Here's just the idea of the atom splitting, where a neutron comes in, hits carbon or oxygen, releases a large number of alpha particles. The alpha particles can be damaging. And what happened, how are photons damaging? The most common process that goes on with photons for radiotherapy is called the Compton process. It was discovered by a guy named Compton, and what he did is he demonstrated that when the photon comes in, it often intersects with the electron in the outer shell of an atom and causes it to be ejected. When this happens, a scattered photon and a fast electron are given out. So the atom loses an electron overall. The Compton process, as I said before, is extremely common, and this is how most of the damage is done. There is a second process, and the second process is probably more important for radiology than it is for radiation oncology, but they do ask it on the boards, and it is of relevance to us. This is called the photoelectric process, not named after a guy called photoelectric. What happens in this process is the photon comes in, causes the ejection of an electron in an inner shell. So remember, the Compton process was an ejection in the outer shell here. Here's the photoelectric process. The ejections in the inner shell. The atom is unstable because it's got a vacancy in the inner shell. So now what happens is this moves out, and the atom works to gain an electron from some other source, whether it's another nearby atom or whether it's from another shell within the same atom. It doesn't matter. The vacancy becomes filled. But this idea of having electrons move back and forth, back and forth, back and forth from one atom to another atom is what allows us to see through matter. And it gives us the basis of the X-ray. So the photoelectric process is the basis of the X-ray, and it allows us to see dense versus non-dense material. The movement of electrons in aqueous substance is much faster than the movement of electrons in a hard material. So when we look at an X-ray through tissue, the tissue is made up of water mostly, so the electrons move fast from one to another. In bone, which is very dense material, the electrons do not move very fast. So we don't see through the bone, we see through the tissue. And that's the basis of the photoelectric process. There are other processes. One other that I've seen on the boards in recent years is this one called pair production. It's not mentioned in Hall's textbook, at least not in the introductory material. It is later on when we talk about the PET. Pair production is the basis of the PET, where you have an electron and a positron produced. They annihilate each other, and that annihilation gives off an energy that we are able to read and becomes important to us for the PET assay. So here are the three most important processes kind of put together. Photoelectric with the ejection from the inner shell, the Compton with the ejection from the outer shell, and the pair production, which has this pair production occurring in all of them. And I just want to note that there's an error here. This photon should be from the outer shell, not the inner shell. There are also many other processes. I've not seen these on the boards. I just don't want you to think we've looked at everything. There is photoinduced disintegration, where a photoneutron results. And there's also the so-called Bremsstrahlung effect. I haven't seen either of these asked on the boards. So here's excitation, where the electron gets excited to a new energy, gives off light and heat. Here's the Compton process. Here's the photoelectric process. And then the Bremsstrahlung X-ray, which Bremsstrahlung means putting on the brakes. As the incident electron comes in, it goes around the atomic nucleus. It gives off an X-ray and a secondary electron, and we can actually read that X-ray. I haven't seen that one asked on the boards either. There was one board's question on scattering, so I put this in there, and this is what they asked. I think this is much more a physics question, and I'm not even sure it was on the biology part of the boards. This was a story told me by one resident. But the question was, does elastic scattering involve the loss or gain of energy by radiation? And the answer is no. Inelastic scattering does involve some change. So that distinction needs to be made. Okay. So now that we're talking about particulate radiations, where are we likely to encounter particulate radiations, and what are their properties? The most common one is going to be either the clinical use or radionuclide. An old radionuclide that was frequently used, is still used in some examples, is radium-226. Radium-226 is radioactive. It decays into radon in an alpha particle. Why do we worry about radon in the home? Because it means that you probably have alpha particles as well. And where do we tend to get radon and alpha particle production? is in basements. Why? Because radon is a byproduct of radium falling apart, but also of uranium and some other radionuclides that we find in the soil. There are areas on our planet, and there are areas in the US that are very rich in uranium and radium, and there are others that are very poor. Chicago area tends to be moderate, and we'll look at the actual levels of radon in different areas. Why is the alpha particle considered to be so dangerous? We're going to look at the kind of ways that we shield against alpha particles, but probably the most important thing I can say is if we have an alpha particle and it's on our skin, we can just wash it right off when we take a shower and it's gone. But if we breathe in the alpha particle and it goes into our lungs and gets trapped there, we have no real way of getting rid of it. And that alpha particle could sit there for years and cause radiation after radiation after radiation, which of course is going to impact things like cancer induction. So that's why people get nervous about having alpha particles around. So there is the negative beta decay, the positive beta decay. I don't think you need to know this about the energy and atomic numbers changing. The most common reaction is if you ate breakfast today, you took in potassium-40, it's in all of our food. There's almost no way to be able to get rid of it. It releases a beta particle, an antineutrino, and a calcium-40, which is not radioactive. So that's why they joke a lot about, how much radiation did you get from your banana today, because bananas are high in potassium-40, and therefore people are being exposed through their bananas. Decay of carbon nucleus, decay of sodium nucleus, I don't think we need to know these so much, but we come down to this point. This is not in Hall's textbook, but it is important for the boards. So the idea is, how do we protect ourselves against ionizing radiation? It depends on what kind of radiation it is. And if you'll remember, alpha particles, I said, were high LET. Beta and gamma are low LET. Alpha particles are so slow moving that if you put a piece of paper between the alpha particle and, so the radiation source is in one location. You have a piece of paper and you have a Geiger counter here or a radiation counter here. A piece of paper will stop the alpha particle from penetrating. So therefore, alpha particles do not stick around very long, and they don't penetrate very deeply. So if an alpha particle is sitting in your lungs, it's going to induce cancer in the neighboring cells, but it's not going to get much out beyond that. So a piece of paper protects against alpha particles. Beta radiation, which most beta radiation is made up of an electron, it will penetrate through paper, but it won't penetrate through a hand or a glove or even plexiglass. So a lot of times when people in a lab are working with a beta emitter, they'll work behind a plexiglass shield, and therefore they are protected from it. Gamma radiation, though, paper won't work, plexiglass won't work. The only thing that works is to put lead in, and that's why we have to have lead shielding against gamma radiation, is because of the potential risks there. Okay. First concept is going to be direct versus indirect ionization. The second is going to be direct versus indirect action. Very different concepts. You need to know both for your boards. Direct versus indirect ionization is really easy. If it's charged, it's directly ionizing. If it's not charged, it's indirectly ionizing. What did we say are not charged? Photons and neutrons. So photons and neutrons, when they enter into matter, what do? They don't carry an electric charge, but they do cause secondarily charged particles to be released that include electrons in the case of photons and protons in the case of neutrons. So photons and neutrons are indirectly ionizing. Alpha particles, electrons, protons are all directly ionizing. And that distinction is all that matters and all you need to know there. Is it charged or not? And here's that example I showed you earlier, where the neutron comes in, causes the recoil proton to be released. The neutron itself is not charged, but the proton that is released is charged. The more important concept that's going to come up over and over and over again in this course is direct versus indirect action. All the time, I'm going to tell you this over and over and over again. The most important target for radiation injury in a cell is the nuclear DNA. So when radiation damages the cell, it causes damage to nuclear DNA. You're going to see consequences like cell death, mutations that are going to result, et cetera, et cetera. If this critical target is hit directly, we call that a direct action. If it's hit indirectly by hitting free radicals, by hitting water molecules that produce free radicals, then that will cause us more damage. Let me show a picture and it'll maybe make sense. So here's the old-fashioned DNA molecule. This is a single strand of it. There's another strand over here. Here's the base. Here's the sugar, the deoxyribose sugar. Here's the phosphodiester bond. And you can imagine, get some sort of ionization event here, and it will cause much damage to that DNA. So here are the two actions. Direct action is where the radiation directly damages the DNA, whether it be the backbone, whether it be the sugar residues, or whether it be the base. The radiation hits the DNA and causes the ionization on the DNA directly. That's direct action. Indirect action is when the radiation hits a water molecule in close proximity to the DNA, gives rise to a hydroxyl radical, and this should actually have an OH dot on it. In some Hall textbooks, it's got the OH dot, but this one doesn't. We'll see a diagram later that does, but it should be an OH dot. And this then can attack the DNA and cause damage. What's the definition of a free radical? It's anything that has an unpaired electron in its outer shell. So the radiation can't interact with any old water molecule sitting inside the cell. If it interacts with a water molecule out in the cytoplasm someplace, sure, it'll produce a hydroxyl radical, but it's not going to lead to DNA damage because that hydroxyl radical is never going to make its way to the nucleus to cause the damage. It's going to be eaten up before then. So therefore, the water molecule must be very close to the DNA. Some people claim the magic distance is 4 nanometers in diameter. So if there's a water molecule someplace in this area, that will cause damage. If it's out here, it won't do very much. And we'll, I'll mention that again in just another minute. Finally, I want to mention that for X-rays, gamma rays, and protons, for low LET radiation, 2/3 of the damage is by indirect action, 1/3 is by direct action. For high LET radiation, most but not all of the damage is by direct action. I again want to emphasize this 4 nanometer radius, 4 nanometer diameter, or the 2 nanometer radius around the DNA is the region where the hot water molecule must exist. And some people believe that it must be a water molecule that is directly touching the DNA that gets a hydroxyl radical in it that creates the damage. So here's just the neutron story, where neutrons have a little bit by indirect action, but the majority is by direct action. And on the boards, and this will come up repeatedly in this course, but on the boards, there are questions that say all damage by neutrons is from direct action. And that's not true. It's most, but not all. If it says most damage, that is true. So be careful how that is worded. And just so it's clear, a single electron track can cause both direct and indirect action all in one track. So it doesn't work only by one or only by the other. Here's just this picture of the hydroxyl radical with the unpaired electron in the outer shell. And the reason why this is so reactive is because nobody likes to have an unpaired electron in its outer shell, and therefore it will work to fill that vacancy somehow. And as I said, this is mostly for water molecules that are directly touching the DNA, not for water molecules that are outside of that diameter. Okay, what does this mean biologically then? Biologically, ionizing radiation comes in, and whether it's by indirect action through the formation of free radicals, or by direct action, working directly on the DNA, we get DNA damage. The DNA damage, particularly if it's low dose or there's not that much of it, can be repaired, the tissue goes back to normal, everything's okay. But if the damage is significant and it can't be repaired, then we can have cell death from it, we can have abnormal repair, which leads to teratogenesis or carcinogenesis. So clearly the effects of these early events can lead to late consequences for the cell. The kind of damage, and we'll talk about this a little bit in our next topic as well, the types of damage produced by ionizing radiation are base damage, single-strand breaks, double-strand breaks, and cross-links. The base damage is the most common. The two most common kinds of damage bases are thymine glycol and 8-hydroxyguanine. Single-strand breaks are next, and double-strand breaks are next. And why are single-strand breaks more common than double-strand breaks? Because a double-strand break is just two single-strand breaks that are in close juxtaposition to each other. So it's a very similar kind of situation. And base damage is by far the most common. Okay, I said already that if the free radical was produced outside of the cell in some distant location, that the cell would actually be able to eat it up somehow. So here we've got the normal cell. The normal cell sustains damage, whether it's radiation or some other type. Free radicals are generated, in particular the hydroxyl radical, which is our most common and most long-lived and most serious free radical produced following ionizing radiation. And this free radical, the hydroxyl radical, now can cause damage to the cell. But there are lots of products that we have within the cell that can eat up free radicals. And some of these you need to know, they're on the boards. Superoxide dismutase, we're going to talk about that a lot. Vitamin C, glutathione peroxidase is going to be very important. We'll talk about that in a moment. Ceruloplasmin, superoxide dismutase, already another form, the mitochondrial form, vitamins E and A, catalase, etc. Why is glutathione peroxidase so important? Well, here's the reaction called the Fenton reaction, where the hydroxyl radicals go to peroxide, go to water. What is the glutathione peroxidase? It takes the GSH sulfhydryl group and converts it to GSSG. So as a net result, any molecule that has a free sulfhydryl group on it can take this OH dot and help convert it into peroxide. So if that happens, what are we going to get? We're going to get less damage for DNA. If we've got a glutathione peroxidase sitting there inside the cell, and we have all this hydroxyl radical that's being generated, and we have all these sulfhydryl molecules sitting around, we'll get less damage to the DNA because it's all going to go into peroxide and into water eventually. So what we normally call this is a radioprotector. And we're going to have a whole section on radioprotectors where we'll talk about them. But I want you to see this now on your boards. Any molecule that has a free sulfhydryl group in it can be a radioprotector. And it's because of this Fenton reaction that that's the case. Another point I want to make is there are a lot of your patients that are going to come through the door and they're going to say, oh, I'm taking my antioxidants. I take them every day. What should I do? Should I go off them when I'm getting therapy or not? Well, there's no real clinically proven data that says one way or another. But I think what most people would say is if you can cope with it, go off the antioxidants for approximately 2 to 3 weeks prior to therapy, because having a lot of free radicals around is actually going to eat up the hydroxyl radicals that are produced by the radiation and probably protect the cancer cell. Now, it's a very small amount that is useful, but still, it's worth noting. Here are a variety of these products that are important, and as I said before, lots of different free radicals that are produced, but the one that is on the boards, the one that we care about the most, is the hydroxyl radical. They end up working in mitochondria. I don't think we need to go into this level of detail here. Here's the reaction again with the glutathione peroxidase here, which now helps to reduce the free radical and create water. Same reaction, similar reaction. There are also processes of lipid peroxidation. Again, I don't think you need to know these in detail, but they're there in case you care about it. Okay, so I'm going to bring up this point multiple different times in the course, and it has to do with the random nature of DNA damage and the random nature of radiation itself. So every patient that walks through the door wants to know, hey, am I going to get a secondary cancer when this is done? What's going to happen to me long term? And the answer we always give them is, look, it's based on probabilities, but we really don't know. And the reason why we don't know is because radiation is stochastic in how it functions. Here is a track of radiation going through. This is a track of electrons. Each dot represents energy that's being deposited, and we can't predict how this track will look. And what we can say is that if this portion of the track hits the DNA, it's probably not going to have much damage, and it's not going to kill the cell. This track up here, if this hits the DNA, you might kill that cell. Or if this portion hits, it might be enough to cause a mutation, but not enough to kill the cell, in which case it could theoretically put the cell a step toward cancer. So radiation has this stochastic component to it, this very random process to it, and it becomes impossible for us to predict effects, and therefore we can't actually answer the questions the patients are asking. Now, there are some other things that we need to mention with regard to time frame following radiation exposure. Yeah, please.
Yeah, sorry, I just had a really quick question about the tracks and indirect and direct action. Is it possible to have a double track effect with an indirect action, or is all double tracks direct action?
No, you can actually have indirect with a double track. You can
How would that work?
It's just that so we'll look at that a little bit in the lecture on LET, but there's some tracks that are branching, and so you end up getting a double track, and the electrons in this track versus the electrons in this track can still hit water and still cause hydroxyl radical formation.
Oh, gotcha. Thanks.
Does that make sense?
Yeah. So basically, it's just depositing its energy right next to both DNA strands in a single track. Oh yeah, that makes sense.
Right. It's like the question is the ionization event on the water molecule or is it on the DNA? And every single ionization event, it's a matter of nanometers as to what gets hit. Does that make sense?
Makes perfect sense. Thanks for clarifying.
Okay, so if we look at the timing of events following radiation, there is what we call the physical, the physicochemical, biochemical, and then the biologic effect. What this in the end means is that the events that happen in the first nanoseconds are going to affect the events that happen in the coming years, even future generations. So the first events in these first nanoseconds are the ionization itself. They lead to the next event, the physicochemical, which are free radicals that are formed. These then lead to DNA damage. The DNA damage can be repaired and you have no problem, or the DNA damage can be misrepaired, in which case you end up with a mutation. That mutation can lead to cell death. It can lead to early and late tissue toxicities, or it can lead to a tumor. If the damage is in an egg or a sperm, it can be passed on for the next generation. If it's in a somatic cell, it can lead to a cancer. And here's the same thing plotted out over time. And you can see that here's the human lifespan, and we could be looking at effects in sperm and eggs that even go beyond the human lifespan. So these first events in the first nanoseconds can have long-term effects. Okay, again, this is not in Hall's textbook, but I feel like if we don't do this early on, it becomes unclear. So I'm going to go through a section now on radiation quantity. Probably you know much of this, so I'm just reviewing it, but I'm going to review it from a biological perspective, so we're all on the same page. So the old terminology was the rad, and it was defined as depositing 100 ergs of energy per gram of soft tissue. And even though nobody uses the rad theoretically today, you got to know what the rad is. There are some questions that are asked in rad, and you have to answer it in gray. A gray is defined as 1 joule of energy deposit per unit kilogram of soft tissue. 1 gray is equal to 100 rads. 1 centigrade is equal to 1 rad. And because of this, there are a lot of old-time radiation oncologists who still think in rads, and they'll talk about hundreds of centigrade of radiation that we're using when they're actually still thinking in terms of rads. Okay. The old use for the exposure, where we talked about the amount of radiation that's in the air, was the Röntgen. We still use the Röntgen. Nobody has shifted that to another unit, but the other old unit, I just said the rad, there was a unit of dose equivalent called the Röntgen equivalent in man, the REM, and then the old unit of radioactivity that was called the Curie, which in actual fact we use most commonly today, because of its clinical value. So this is the breakdown. Let's look first at absorbed dose. We said this already. Old was rad, new is the gray. 1 gray equals 100 rad. Equivalent and effective dose. We're going to talk about this in a moment, but the old was the rem, the new is the sievert, and 1 sievert is equal to 100 rem. So these changes of 1 to 100 are common. The units of radioactivity, however, are different. The old was the Curie, the new is the becquerel. 1 becquerel equals 27 picocuries, 1 Curie equals 37 gigabecquerel. Why did anybody change it? The fact is, in the clinic, in the hospital, when we're giving brachytherapy or something else, we always talk in Curie. We don't talk in becquerel. Why did they shift to becquerel? Because of radiation accidents. It became so hard to work in these small units that you need to for accidents in Curies, which are big units, that they shifted to becquerel. So by tradition, most radiation accidents, we talk about becquerel. Most radioactivity used in the clinic, we talk in Curies. And here's now the official definition. The becquerel is the standard international unit of radioactivity. It gives 1 transformation event per second. The gray is 1 joule of radiant energy per kilogram. And now here's the sievert. And I'm going to do my best to explain sievert to you. We're going to have it again later. It's always a very complicated term. And the way I usually define it is based on some old experiments I used to do. So I used to be out at Argonne. I used to work. I had a reactor underneath my office, and I would go down and work in this reactor, and it was a neutron reactor. And of course, the first experiments you do are to ask the question, how do the neutrons compare to X-rays for their amount of killing? And what I found was that for neutrons, I would get the same amount of killing, about 10% of the cells, with 20 centigrade of neutrons as I got for 1 gray of X-rays. What did that mean? That meant that the neutrons were 5 times more effective at killing than the X-rays were. But what that means that when I talk about dose of dose of neutrons, that I don't understand it very well. So what we do is we, by convention, convert everything for all radiations, neutrons, alpha particles, etc. We convert them to what they would look like in X-rays, and we call that a sievert. It's the term for equivalent dose and effective dose. And I'll show you the formula in just a minute. I want to make a few other comments about absorbed dose before I do that. This is the Röntgen definition. I've never seen this asked on the boards. I've actually never seen Röntgen asked on the boards. Here's now the dose equivalent. The old term was the rem, the new was the sievert. What was done in the old days is they would say 1 rad times the relative biologic effect would give 1 rem. And they compared everything to X-rays, just like I said for those neutrons before, right? That the neutrons were 5 times more effective, so therefore the dose would be, the amount of damage would be 5 times more, so therefore the sievert would be 5 times more. So people came up with this formula, but instead of using rem and rad anymore, we do sievert and gray, and RBE was used. If this doesn't all make sense now, I'll explain it again later, but I want to still explain it now too. RBE is an experimentally determined number. I want to know RBE. I go into the lab, I do a measure of the RBE. And I do exactly that experiment I mentioned, where I compare what do the neutrons versus X-rays cause for cell death, and there we go, I get an RBE. So it is experimentally determined. The problem is, when do we need to use sievert most often? We need to use it in accidents. It's normally a measure used for radiation protection, not for what we would use clinically. So if I want to do that, I don't have time to go into the lab to do all the experiments to figure out the RBE. So instead, we have some legislatively determined numbers called the weighting factor, also the quality factor, which we can use, multiply that times the dose in gray to give us the dose in sievert. So my neutrons would cause 5 sievert. They were a dose of 5 sievert when you absorb them in the body. The gamma rays, X-rays, were 1 sievert because the radiation weighting factor for X-rays and gamma rays is 1. So sievert and gray are the same for X-rays and gamma rays, but they're different for, even for protons, they're slightly different. For X-rays, for gamma, for neutrons, for alpha particles, they're also very different. Here's the conversion table, and this conversion table of Becquerel to Curie and Curie to Becquerel. I would use this one. It's hard to remember what a picocurie is, but it's easier to remember that if you get a Becquerel, it's 2.7 times 10 to the minus 11 Curie, and vice versa. So these are the ones I would memorize. All the rest of these are just conversions on a per basis. Here's again the Röntgen, another definition. Some information on half-life, which I don't believe you need to know for your boards anymore. It's there if you want it, but you don't need to know it. Okay. And now finally we come back to the concept of sievert. So here's the actual formula where the relative biologic effectiveness, if it was done, say, for neutrons, is where you would take the dose in X-rays, and remember I was getting about 1 gray or 100 centigrade, divided by the dose in neutrons, which is about 20 centigrade, and I would get an RBE of 5. So then I would take the gray times the quality factor, and get the sievert. Here are the quality factors that we are using today. For photons and electrons, they're always 1. So you take the gray, you multiply by 1, and you get the sievert. No problem. For thermal neutrons, it's 5. For neutrons, it's 20. For other charged particles, it's 20, except for protons. And protons, there are always fights going on about what they are. I think that the convention used is that they're 2, but actually they have an RBE of around 1.1 or 1.2, so they're not all that different from X-rays or gamma rays. We'll talk about that in a lot more detail, both in our RBE lecture and also when we talk about protons and neutrons as therapeutic entities. Here are some of our values for absorbed dose, etc. And now finally I get to the point where I try to put all of this in perspective for you. So we just said that for gamma rays and X-rays, 1 gray is about equal to 1 sievert. So what is our average natural background in the US? The natural background in the US comes from gamma rays and X-rays and from alpha particles resulting from radon. This is about 2 millisieverts per year, which would be, if it were X-rays, 1 milligray per year. And here, the natural background from terrestrial radiation, cosmic radiation, and radionuclides that we ate today, these are all about 1 millisievert per year. So at the end of the day, and you got to know this number, our natural background in the US is approximately 3 millisieverts per year. Does everybody get 3 millisieverts per year? Nope, that's the average. There are some places where there's really high radon and they get a lot more than 2 millisievert per year from radon. And then there are other areas where there's almost no radon and there's less than 1 millisievert per year from radon. So the natural background in the US is 3 millisievert per year. We set our dose limit for the general public as 1 millisievert per year over and above that. What's the problem with the dose limit for the general public a lot of times is that we can't separate it from the natural background, but it is over and above the natural background. And then here are some examples: CT scan, chest x-ray, dental x-ray, full mouth, cross-country, airline flight. These are the things that are likely to contribute as well and give you a basis for comparison. So, when your patient says, oh, I'm not going for that CT, well, you can say it's like natural background in a year, not even. So you can try to put it in perspective. Here are some reactions of peroxide with water. I don't think you need to know the radiochemistry here, but it does bring home the free radicals. And as I mentioned already, the single strand breaks, double strand breaks, base damage, and there are some cross links as well that come from ionizing radiation. I guess I should say this here, and I'll probably say it again later, that there are no characteristic lesions in the DNA from radiation damage. UV radiation often causes T to A transitions. So if we see a genomic sequence that changes T to A, we can usually assume, what it might be, that it might have come from sunlight. But for ionizing radiation, there's nothing. It causes single strand breaks, double strand breaks, base damage, just like almost any other DNA damage agent might do. And there's nothing that's characteristic. So much as the the federal government would love to be able to say, whoa, this guy's claiming he got his radiation exposure from military work, his cancer from military exposure, and they'd love to disprove that. The fact is they can't, because there are no special mutations and no special characteristics that come from radiation. There will be some special kinds of cancers that come from radiation, and we'll talk about that, but that's about the best we can do. Here's penetration. We'll talk a lot more about this later. I'm not going to go into it now. Here are official definitions: gamma rays, X-ray ionization, electron volt, et cetera, et cetera. It's all here in case it's useful. And then here's the summary on this topic. Radiation damage can be by direct action or by indirect action. The direct action is through the direct attack of the DNA itself. The indirect action is usually by producing a hydroxyl radical by damage to water that is close to the DNA. The major target for radiation damage in the cell is nuclear DNA, while there are lots of other targets, such as what one might find for in mitochondria and elsewhere. The most important for us is going to be nuclear, and base damage, cross-link, single-strand breaks are all the kinds of damage that we might see in cells following radiation exposure.